In contrast to the intelligence of people or animals, artificial intelligence, AI, refers to the intelligence of computers or software. Advanced web searches like Google Search, recommendation systems, voice recognition software like Siri and Alexa, self-driving cars like Waymo, generative or artistic tools like ChatGPT and AI art, and competing at the highest levels of strategic games like chess and Go are just a few examples of AI applications. One of the coolest developments in computer vision is the new AI model TAPIR, which was developed by Google DeepMind researchers. Artificial intelligence computers' vision field focuses on comprehending and evaluating visual data, including photos, movies, and live feeds. Its models are capable of incredible feats like face recognition, object detection, scene segmentation, caption generation, and many other things. These models can assist us in deriving valuable insights from diverse media types and applying them to a variety of applications, including security, entertainment, education, healthcare, and others. However, how do computer vision systems work? To learn from vast volumes of data and extract traits that are pertinent to the task at hand, they employ deep learning algorithms. For instance, if you want to be able to recognize someone's face in a picture, you need a model who can learn to recognize the major features of a face, such as the shape of the eyes, nose, and mouth. Then you require a model that can match the best features of the faces in your database with those of the faces in the photo. Easy, right? What if you wanted to track a particular spot on a person's face or any other item in a video sequence? What if, for instance, you wanted to follow the center of someone's pupil or the tip of their nose as they moved around in a video? Things become complicated at this point. Tracking a point in a video is more difficult than finding it in a single image, as you can see. Occlusion, motion, blur, changes in illumination, size differences, and other difficulties must be overcome. These elements may make it challenging for the model to follow the point when it switches between successive frames. At this point, the TAPIR enters the picture. Tracking any point with per-frame initialization and temporal clustering is known as tapiring. The point can be on a person's face, a car's wheel, a bird's wing, or anything else. The new model can successfully follow any point on any physical surface throughout a video sequence. It can manage everything. A group of researchers from the University of Oxford, Google DeepMind, VGG, and the Department of Engineering Science developed it. On June 14, 2023, they released their article and posted their code and pre-trained models on GitHub as open sources. How well does tapiring operate? This method has two stages: a matching stage and a refinement stage. In the matching stage, it examines every video frame separately in an effort to find a candidate point that matches the query point well. The moment in the video sequence you want to track is the query point. As an example, your query point would be the tip of someone's nose in a video. An image patch surrounding the query point is used as input, and a deep neural network produces a feature vector that reflects the appearance of the query point as output to determine the candidate point match for the query point in each frame. The most similar feature vector is then selected as the candidate point match after this feature vector is compared to all other feature vectors that could possibly exist in each frame using cosine similarity. In this manner, the TAPIR can determine which point in each frame is most likely related to the query point. Because of this, it can withstand occlusion and motion blur even if the query point is obscured or unclear in some frames. On the basis of its look, it can still determine the closest approximation. Finding candidate point matches, however, is insufficient to accurately track the query point. You must also consider how the question point changes over time and how variables in illumination or scale affect how it appears. The step of refining begins here. It is here that, using local correlations, TAPIR updates both the trajectory and the query features. The query features are the feature vectors that describe the query point appearance, and the trajectory is the path it takes during the video series. Another deep neural network is now used to update the trajectory in the query features. This network receives input as a small image patch surrounding the candidate point match in each frame and generates a displacement vector that specifies how much the candidate point match should be shifted to more closely match the query point. The candidate point match is then refined to produce a point match that is more closely related to the actual query point by applying this displacement vector to it. To put it simply, the system analyzes small portions of an image to determine how much a picked point has to be adjusted to match a target point before bringing the selected point closer to the target. Averaging the feature vectors of the improved point matches over time allows TAPIR to also update the query features. By integrating these two steps, it may adjust to query point's appearance changes and keep a consistent representation of it. It can accurately and precisely pinpoint any point in a video sequence. It can handle films of varied lengths and qualities and simultaneously track several points. How TAPIR's performance in certain benchmarks and demonstrations. The TAP-Vid benchmark, a standardized evaluation dataset for video tracking activities, was used by researchers to assess TAPIR. It features ground truth annotations for 10 points per film and 50 video sequences with variously shaped objects and settings. They evaluated TAPIR with several baseline techniques, including SIF, ORB, KLT, Superpoint, and D2Net, a parameter known as average Jacquard, AJ, which is the average intersection over union between the projected point positions and the ground truth point locations, was used to gauge performance. According to the findings, TAPIR fared significantly better on the TAP-Vid benchmark than any of the baseline techniques. Its AJ score of 0.64 is almost 20% higher than the second best approach, D2Net, which had a score of 0.44. This indicates that, compared to previous tracking techniques, the TAPIR was able to follow the dots closer to their actual locations. Additionally, it did well on the Davis benchmark, which uses a dataset for video segmentation tasks. It offers ground truth annotations for pixel-level segmentation and includes 150 video sequences with various types of scenes and objects. Davis was tracked by the researchers using TAPIR, which tracked 10 points per video, and they generated the AJ score as usual. In comparison to the second best approach, D2Net, it received a score of 0.39. They discovered that TAPIR obtained an AJ score of 0.59, which is again nearly 20% higher. This indicates that, compared to previous methods, it was able to follow the spots more consistently throughout many frames. Benchmarks, however, do not adequately convey how great TAPIR is. You must experience it yourself. You can run TAPIR on your own videos thanks to the researchers' 2 online Google Colab demos. The first sample, known as the TAP-Vid demo, enables you to upload your own video or select one from YouTube, after which you may choose any point on an item in the initial frame that you wish to track throughout the film. TAPIR will then be applied to your video, and the results will be displayed to you in real time. Using your own webcam as the input source, you can choose any place on your face or any other item in front of you that you wish to follow live as you walk about in the second example, which is called the webcam demo. The results are then displayed in real time as the tape is being played on your webcam stream. Both demos are crazy. If you experiment, you can see how tape can follow any point on any object with the astounding accuracy and precision despite obstructions, motion blur, changes in illumination, scale, and other factors. In fact, it's intriguing. A superintelligence is a hypothetical agent whose intelligence would be significantly greater than that of the smartest and most talented human mind. Software that is sufficiently intelligent as a result of research into artificial general intelligence may be able to reprogram and enhance itself. Recursive self-improvement would result from the improved software being even better at improving itself. Its intelligence would drastically expand during an intelligence explosion and would significantly surpass that of humans. This situation was dubbed the singularity by science fiction author Vernor Vinge. The technological singularity is a point beyond which events are unpredictable or even unfathomable, since it is difficult or impossible to know the boundaries of intelligence or the capabilities of superintelligent computers. That's all about today's video. It's really curious to know how TAPIR can improve in future experiments.